Welcome to the lesson 6. Here we will go through 3 examples to see how the principles of contract design apply to various applications and how TON platform helps you to build scalable and secure applications. We'll start with tokens. As you recall, in Ethereum or even non-blockchain implementations, the tokens would be implemented as a simple ledger of the accounts. You have a list. The program controls this list of accounts, and each item in the list is effectively the address of the participant and their balance. This is pretty simple, but unfortunately it doesn't scale in the blockchain context because your smart contract has to continuously grow with the number of users and becomes more expensive for each user to interact with. Now, what is the TON approach? In TON, the tokens are implemented as distinct contracts, one contract per user plus a separate minter contract that provides the interface for creating new units of the token. The contracts per user are called Jeton wallets. And the job of those Jeton wallets is to hold the balance of a token for each individual user. And they have a very interesting trick to authenticate transfers between them, because this is what happens in those tokens. Whenever the user wants to transfer a token from one account to another, they send, first of all, an external message to their wallet. Then this wallet unwraps this external message and sends through the internal message to this user's Jeton wallet, saying, please send the money to certain address. Their Jeton wallet decrements their balance by the necessary amount and sends the message to its sibling contract that has exactly the same code, but a different owner. And this message says, please increment your balance with the same amount. Jeton wallet of the recipient user verifies that this message was authored by its sibling and sends the notification transaction to the wallet of its owner. And in this system, the logic, the atomicity of change of the hands of the token is broken into 2 separate transactions. So strictly speaking, it's not atomic, but the rules of the network guarantee you that these balances will be in sync eventually, and there will never be a point in time when both accounts have the same amount all at once. How does it work? If you look back in the lesson about authentication, you will see that there is a so-called DNA check. This is where one Jeton wallet checks the message sender, not directly against its own trusted address, but it actually computes this on the fly using its own code that it trusts and the data provided by the sending contract. So what happens is that one Jeton wallet, when it's receiving a message saying, hey, could you please increase your balance, it verifies that the message came from the contract exactly like that, with exactly the same code, and therefore it implicitly trusts that on the other end, the balance was decremented. If the code was different, then of course anything could happen there, and the Jeton wallet rejects such a message. Now, this system allows really infinite scalability of the token operations because you may have millions of users, and each of the Jeton wallet will exist potentially in a separate shard chain, and transactions in between those Jeton wallets will also be independent from each other. And they don't have to go through a single minter contract. They could stay local to their own shard chains. And you can use this principle to implement your own custom tokens. You don't really have to use only the standard. This is really just the trick using the facilities that the TON blockchain provides you. The second example I wanted to talk is multi-signature contract. In a multi-signature contract, you have multiple parties that have to authorize certain action all together or with some threshold. Let's say you have 3 friends and 2 of them need to authorize transfer of coins or tokens or send any instruction to a decentralized exchange, let's say. Now, this multi-signature contract on the first side may be implemented with just a simple list of participants and process all the messages right within itself. However, there lies a slight problem. how do you keep track of the pending requests and how to manage the situations where one of the parties becomes malicious and potentially creates too many requests and increases the state of your contract? Traditional approach would be to implement some kind of limits, make your storage more complicated. But in TON, you can make it even simpler and more scalable and avoid a lot of extra workarounds altogether. But in TON, you can avoid all sorts of workarounds altogether and make your contract even simpler by tokenizing the requests that the users send to this contract. So let's say you have this small list of people and you can still just store this list in the contract. No problem with that. It could be like 3 or 5 people. But then anytime any person wants to initiate any action on the contract, they would send a message to initiate this action and receive in return a unique token that encapsulates this request and encapsulates also the votes for this request. And now this token belongs to this user. They cannot change its contents how they want because it protects its own state. But they're paying the rent fees and the gas costs for operations in this token. And now if some malicious user wanted to create 1 million requests, then there's no problem with that. They would create 1 million tokens and they will pay for all of them. And all other users of this multi-signature contract would not be bothered in any way. But if it's an honest user, they will create this object and then ask others to provide their votes. So others would send messages to this new temporary object that will increase its count of votes, and when it reaches the threshold, will send the message back to the multisig and say, hey, I received the number of votes, could you please make this transfer? And the multi-signature, just like with the Jeton wallets, will check the authenticity of this request object and forward their message. And this way, this tokenization was applied not to individual users' share or a share of the value or share of the contract. It was applied to just the temporary state of a system. And by doing that, you dramatically simplified your logic and protections against denial of service because you just didn't create any loopholes for denial of service in the first place. And this is, I think, an important example that you should keep in mind when you apply tokenization more broadly than just to the storage of the value. The third example is the user's wallet itself. And since the wallet version 4, the wallets support the plugins that enable people to create subscription payments. And this is a very powerful feature, and it scales relatively well because the user controls this list of plugins. But we could imagine a better way to do that. So the way the plugins are implemented in the wallet version 4 is by storing individual contract addresses in the list. So if you have 100 subscriptions to 100 services, then you will have a list of 100 items. And that is slightly problematic for the user because now the cost of storage is higher for their wallet, and every time they make a transaction or anytime the plugin requests the money from the wallet, they have to go through a larger list of plugins, and this incurs extra cost. Now, what we could do better here? One idea is that instead of listing particular plugin addresses, you could list distinct code implementations of those plugins. And if they share the same code, there would be just one record for any number of subscription plugins that you have. So for instance, if you're extending your wallet functionality with 2 sorts of plugins, then you will have 2 pieces of code with any number of plugins that actually uses those pieces of code. And inside this code, you would have to add something what we already discussed with Jeton wallets and multisig. You would have to ask the mutual authentication. So on one hand, the plugin contract should authenticate that it was created by a proper wallet, so that the wallet trusts that it didn't receive the message from a rogue contract created by a malicious actor. And the wallet itself checks that the code of this other contract belongs to the list of plugins, and therefore it can trust that the code was good, it did its own checks within that code, within the plugin, and then that the message was sent from some contract that was deployed with the trusted code. And this, a little bit of an extra logic, seems very similar to how tokens work, allows us to dramatically reduce the amount of storage necessary for storing the plugins in the wallet, and also allows us to push the cost of operating those plugins to the actual parties that are interested in them. So typically those are subscription contracts, and on every end of the subscription contract you would have some sort of merchant or service provider who is drawing money from it. And so now it becomes their own problem to keep this contract alive and pay its rent and keep necessary balance on it. And from the user's perspective, they could have a very short list of supported extensions in the wallet while not worrying about the liveliness and the number of subscriptions that they created. And so this is the overview of 3 situations where we could apply our principles of scalable contract design. And I thank you very much for attention. See you in the next chapter.